So far, we just looked at the gain descent, the property of the negative feedback. We just looked at the first three items: gain desensitization, terminal impedance modification, and bandwidth expansion or modification. We just looked at. Now the remaining two is nonlinearity reduction and noise suppression things. This is also important to understand. Okay, we'll see that one by one. Another property of the negative feedback is the nonlinearity reduction. For example, if your open loop amplifier gain is shown as like on the left, so its gain characteristic is very nonlinear. At the low signal amplitude, you get the A1 of the gain. In higher signal amplitude, you get the larger gain, A2. As you can see, this is a very large, typical nonlinear gain curve. So if you apply the signal through this amplifier, you will get large distortion. But after your feedback is applied, your closed loop gain is what? H of S is A0 over 1 plus A0 times loop gain beta. So if the A0 is large enough, then we can make it close to 1 over beta. So after feedback is applied, your overall gain is like close to the 1 over beta like this, regardless of the A0 nonlinearity. So overall nonlinear characteristic is suppressed greatly, right? So it is important to implement beta, feedback factor beta, is implemented in passive element, like passive element. Why? Because that is very linear, right? Your active device like a transistor is very non-linear, right? If your signal is large, your current and voltage relationships are not linear relationships. So for the feedback, you have to use the linear elements like RLC, right? Passive component. All these are used in the feedback. Okay. We can actually calculate how much nonlinearity is improved. So for a certain amplifier characteristic, for example, if your amplifier is like A0, can be represented A1 times X plus A3 times X cube. So in that case, so the third order distortion here, right? Third distortion. In ideal case, we want to have a linear amplification gain like A1 times X, right? But as you can see, most of the typical, for example, the differential amplifier, you know that your gain characteristic is like a compressive like this, right? As the signal getting large and large, your gain is kind of a diminishing, getting down, going down. So we can model that characteristic like this, kind of a third order polynomial equation. And then we apply the beta here. Now we can calculate the overall closed loop equation, right? So based on that, so we know that AX over 40 gain, right? 1 plus AX A times beta, right? That's A times beta, like that, right? So this kind of equation will be nonlinear, we know that. So we can represent the nonlinear equation y and x relationship, input and output of the closed loop system you can represent that like this, right? Alpha 1x plus alpha 2x squared plus alpha 3 times x cubed plus something like that. Now let's find the coefficient alpha 1 and alpha 2 and alpha 3 around the 0, right? So without feedback, we know that coefficient is small a1 and a3 like this. After feedback, the non-ideal component, the coefficient is like alpha 2 and alpha 3, etc. Right? So we know that A is the something like input. Here is what? X minus beta y, right? A is x minus beta y times a1 plus a3 times x minus beta y cubed, right? This relationship. So from here, we will try to find the alpha 1 and alpha 2 and alpha 3 by having some Taylor theory, right? So take the derivative and find the coefficient. In general term, we can have the coefficient, Taylor coefficient, we can find through this kind of a relationship, okay? So you have to take the derivative multiple times to get the certain coefficient. This is the actual summary, or the derivation that you would have. So here the alpha 1 is a1 plus 1 plus a1 beta. This is exactly the same equation that we would expect from the feedback for the first order coefficient. And for the second order nonlinearity coefficient, alpha 2 is equal to 0 because the original amplifier was third order distortion. It had only third order distortion. The second order distortion term goes down, becomes negligible. This happens typically in differential circuit. So in differential circuit, the dominant nonlinearity source becomes the third order rather than the second order distortion. So now find this third order coefficient. So we derive all the equation around the 0. So we'll get like this. As you can see here, the original third order distortion was A3. As you can see this example, the original third order distortion coefficient was A3. Now after feedback, the third order distortion coefficient becomes what? A3 over 1 plus A1 times beta fourth power. So as you can see here, the third order distortion suppressed by the loop gain, right? How much? 1 plus A1 beta times the fourth power to the power of a 4, right? So as you can imagine or the guess, here again the loop gain A1 times beta. As long as loop gain is strong, if the loop gain is strong, right, we can strongly suppress distortion is suppressed well, right? Okay. Now let's compare with the first order, the original, for the first order coefficient was A1, and after feedback, that one become A1 and 1 plus beta times alpha 1, right? So you can see the difference between the first order coefficient, this is the gain, right? Linear gain versus the third order. So you can see the difference, and you can see the ratio, how much larger or how much got lower, it got lower by 1 plus what 1 plus the alpha 1 and beta cube, right? So first order kind of the previous like this relationship, but we got more like so exact coefficient like this a3 over a1, right? a3 over 1 was what reduced this much, kind of the third order is reduced, right? Now let's take a look at the impact on the noise. The as you can imagine, the amplifier input reference noise voltage is modeled like this, right? Now let's try to find the transfer function from x to y. So overall like this, y equal to what? X minus beta y. Here this is beta y, right? And then additional noise plus Vn and the times A. So if you write down all, then the what? From noise to the output response will be like this. And this is plus x. What about x? X is again 1 plus a beta times a, right? So we have a signal and noise seeing the same gain, meaning it shares the same response, right? A beta 1 x plus Vn, right? So what it means is that times x, no. So what it means is that the noise inside the loop is same as noise outside of the noise to the input, right? So basically this is equivalent to what? A beta n x and y, right? So noise of the amplifier contribution is just the same as the just taking out of the loop is also equivalent, right? So the amplifier noise inside the loop, the feedback loop noise doesn't change the noise characteristics. So input reference noise in feedback is same as the amplifier's input reference noise, right? This is something that you can think of, right? So negative feedback. So inside this this noise in the inside the feedback can be just modeled as outside of the feedback, as I shown before, right? Shown here, right? So the input reference noise is summarized like this. So output inside the input here the noise is injected here at input, because all the noise of the amplifier can be referred to the input, right? So once that has happened, so output overall closed loop response will be like this. So the noise is added on top of the input. Now the question is, the thing becomes different. So if you add noise at the output, let's say at the output n, what is the transfer function output over n? That would be what? So for the path gain is 1 and 1 plus n, the loop gain is a1 times beta. So in this case, if the noise added externally, the external noise here is suppressed by the loop gain, right? Noise is suppressed. Noise is suppressed in this case. So the external noise is added at the output, the overall transfer function like this. So the noise is suppressed by the large loop gain, right? These are some of the exercise that we may think of. For example, the diode connected load. We have, let's say, register feedback like this. We have the register noise 4KTR, right? VN R square, mean square, and noise voltage would be like this. Since this is kind of inside the feedback, the drain and gate is kind of connected through the R. The noise can be just coming out of the loop like this. So those are equivalent model. And also, for example, like this kind of amplifier, inverting amplifier, noise of this guy at the input. This noise source can be out of this negative feedback. Then once that it becomes out, then it would be like this, right? R2 minus plus V out. So now the noise from the output response would be, we can change the location of the register R1 and R2. So like that is equivalent. So N, right, like this. So you can find easily the gain of V out would be minus R1, R2, R2 over R1 times Vn, right? So this corresponds to the output noise power would be amplified the version of the OPM input reference noise, right? So this is something that you may utilize easily. There are many feedback amplifier topology. For example, in the undergraduate course, we had learned about the OPM feedback circuit like this. This is the inverting amplifier. We have an OPM here. And also we can have a capacitive inverting amplifier. So amplifiers, the simplest amplifier is 5 transistor OTA here. So in this case, the output impedance is large. So if you remember in the undergraduate course, we had to assume that for the ideal OPM amplifier has a characteristic of the R out equal to 0, right? But this is the OPM. For the OTA, the output impedance is large. Still, it is fine because most of the on-chip buffer has its load impedance is not the resistive load. It is most of the case is capacitive load. So their DC gain is not collapsed at all. So we can use the OTA structure for capacitive load. So sometimes this kind of OTA structure can be said the OPM, right? In that case, the output load is capacitive. So with CL, capacitive, right? So in general term, the OPM output impedance must be 0, right? In that case, it is considering also the resistive load as well, right? And also we have a OPM here, resistive load feedback here. In this case, still the R1 and R2, we assume that R1 and R2 is quite large, much greater than RO, right? Output impedance, that would be what? ROP in parallel with RON, so that the DC gain is maintained. Otherwise, the OPM gain will be collapsed. So the loop gain will collapse, right? So in that case, the negative feedback becomes doesn't work. That doesn't work. So the feedback analysis or what we assume is not valid. So another example, we had the feedback through the gate and drain like this. So this kind of thing is sort of the amplifiers. So we have a resistive feedback, RS and RF like this. And also there are many different kinds of the feedback structure we can imagine here. All these kind of technique is used in actual amplifier. So this is the feedback amplifier that we had learned so far as quite important. The concept and principle and its application must be well studied. This kind of feedback circuit is kind of, if you think of the circuit designer, the circuit designer must be very knowledgeable on this kind of feedback topology. So we will see more as we go through the rest of the course. Okay. As you may have noticed that there are many different topology. So in our feedback analysis, we were simplifying everything like feed forward gain A and feedback factor, feedback gain beta, and plus and minus at the input, subtractor there, something like this. So every signal it had a quantity. We have just multiply the quantity and subtract the quantity. The amplifier output will be like this kind of output will be what, A times the x minus beta y. So all these seems clear in mathematics, but the problem is in the actual circuit we are dealing with both terminals. So here we are talking about the only signal, but in circuit, inside the circuit, the negative feedback, we have to deal with the voltage and current. And on top of that, also impedance, as you can imagine. So the V equal IR, whatever, V equal IG, whatever, right? So there's some relationship, all these between those the values. Sometimes we treat the signal as a voltage, sometimes we treat the signal as a current, right? So depending on whether that signal, our signal is voltage or current, our analysis becomes more not clear. So because our amplifier gain is affected by the load impedance. Let's say even though you design the gain of A, if the beta, the feedback network, loads the amplifier output, then it may have a different amplifier gain. So for example, if you have a resistive load at the output, your output gain and amplifier gain will be collapsed by the resistive load, right? And also the current, if your input is current, then you may have to input signal is current, you may have to consider the subtracting the current rather than the voltage. All these things are very complicated. We have some of the categorization, like a feedback affected by loading, and also ambiguous decomposition like this. And this will affect the load gain, feed forward gain. That will affect the feed forward gain and the loop gain and the feedback factor. All these, and also canonical topology like this. In the middle, we have a common source amplifier with the degeneration RS. If you remember the gain of this kind of amplifier, we have a GMRD without RS. This RS has some kind of negative feedback action. So GM times RS. The overall gain is reduced by the loop gain here. Inside we have a loop inside the gate and source and ground. In this loop there is some negative feedback action, right? If you remember, so the output is current between drain and source. For example, voltage, let's say if the gate voltage go up, this one trying to follow to go up, but the resistor, because of resistor, the current try to increase further, right? By if the source node go up, the current through the RS goes up, right? So the without RS, if the RS is equal to 0, if the gate voltage go up, it will directly affect the drain current. But with the RS, the amount of voltage change will be reduced, right? Compared to RS equal to 0. For the non-zero RS, the amount of voltage variation on the source will be reduced by the negative feedback, right? I mean the amount of voltage difference between VGS, right? So VGS will be affected, right, by the RS. If the RS is infinity, VGS becomes, so if the RS becomes infinity, then VGS, small signal variation, will be small. For the RS equal to 0, VGS will be directly coming from Vin, right? So this kind of some negative feedback action altered, change the current in response to the voltage variation inside the circuit. Okay. So we will see some of the example when you break the loop inside the circuit. For example, if you have this kind of amplifier structure, you wanna break the loop at that point. But reality, what it happen is that you cannot just disconnect the circuit when you analyze the open loop gain, if when you calculate the loop gain, because the impedance is already there. So when you, for this amplifier, common source amplifier, we are looking at the RF. So when you break the circuit, you have to consider the impedance on the left and right, the breaking point. The amplifier was looking at RF, and also input side it was looking at RF. So all these kind of impedance loading effect must be considered when you break the circuit. This is another example when you have this kind of negative feedback. When you break the loop here, you have to also consider the loading RF and RS on both sides like this. So this kind of identifying this kind of loading effect, it would not be easy for you guys. So so we would just having a rough idea for here. We'll just stop here for just when you analyze the feedback. You know that when you change some component, it will make this feedback stronger or weaker. If you can have a sense of the having stronger feedback by having larger gain internally throughout the loop, then your circuit becomes more negative. It will become more following the negative feedback properties. Okay. All the details described, the more complicated analysis are described in the Rajav's textbook, but we would not go through that all the details because all those are related to the mathematics and it's based on some assumption. Those practice may not give us a good insight when you design the circuit or analyze a circuit. So I would personally, I would not recommend to the exercise or spend too much time to having the concept of all different kinds of negative feedback analysis. What you can do is that without have, so what you can do is that just you can solve your circuit. For example, for as you solved in the common source amplifier here, you know the input to any circuit network, whether it has the feedback or not, you can drive the equation and you can find out, right, V output over V in, right? So if you can find out the relationship or equation, you can look inside the what is actually affecting gain and how we improve the gain or characteristic. You can once you find out the equation, you can figure out how you can improve your circuit, right? Let's take a look at some example of the negative feedback circuit here. This is constant current generation. So there is a negative feedback here. Let's say if the output, this node voltage go up, then the amplifier goes down and output goes down. So this is kind of a negative feedback. The output current I out will be inside. Once the negative feedback edge is settled and stabilized, the difference between input and the feedback voltage will be zero. So the 0 times very high gain, like infinity, will give us the constant value at the output of the input, the output of the amplifier. Here the once, because the V in and is applied here, and the feedback, because of the no DC voltage difference here, so the feedback voltage will be V in. So the current through RE would be V in over RE. This current will directly flow through the device, and then I out would be V in over RE. The loop gain here is that from gate to source is kind of approximately a gain of 1. So approximately times 1. So the amplifier gain A0. So if you, as long as we make the A0 large enough, then the loop gain is very strong. And the input impedance becomes the infinity because the capacitive, there's no resistive component. The overall out impedance by this kind of a negative feedback, so our resistance would be increased by that the loop gain. The output impedance was what from the conventional common source stage with the degeneration. The output impedance is what RO 1 plus GM RE. So this impedance is boosted by loop gain, by the feedback, taking the feedback here, right? So this is one of the example that you can boost the output impedance even higher. So this kind of an example is popularly used in the reference current generation. So you have like this circuit, and take the current meter here, like this. So the desired current level is set by this negative feedback, and that current level is replicated like that. Okay, VREF. This external VREF will be up across the RE, so current would be like current IRE would be set by like that, right? Another example that we were looked at before is the common source degeneration. So as you imagine that conventional differential pair input linear range was limited to square root of the overdrive. Once we have the source degeneration, which is we were extending linearity region by how much? Root 2 V overdrive plus RL times the 2I bias, right? This is the kind of one way of having negative feedback. For example, if your input goes up without RS source degeneration register there, this voltage source node voltage was fixed, but with the source degeneration register there, when the input goes up, this will follow a little bit. So the voltage difference between gate and source is diminished. So the output response current is somehow reduced by the negative feedback. So here the loop gain is GM times R. So if the loop gain is large, our degeneration kind of thing becomes more effective. Okay. In this case, if we wanna have a more stronger feedback, we can apply some active gain out of this mechanism in the next slide. This is a more active example, more loop gain involved. On the left hand side, the typical source degeneration here, we apply the gain stage here, right? So here the loop, the signal comes in, then amplified here, and the feedback coming back. So this current, for the input changes, current flows through the internal device, because AC current only flows internal device, because the output side, the other side, is a fixed current level, so no AC current variation is allowed, right? So all the variation flows through here. The shared in gate voltage on the left and right, it replicates the current current. So this kind of additional local feedback loop more linearize the response. One step further, we can have OPM. OPM has a very high gain, like almost infinity of the gain or whatever. So if you make this kind of a negative feedback, try to force that the voltage across the register is same as VP and let's say VN. So this becomes VP and VN. So current generated through this register will be totally linear, right? So as you can see, the feedback strength, as the feedback strength gets stronger and stronger, you can get the more benefit of the negative feedback characteristic. So okay.